Hi everyone, in this video we're going to be talking about algebraically defined vectors and the dot product. So in the last video we talked about geometrically defined vectors. This time, algebraically defined vectors, we're going to be computing things like, for example, the dot product is something we're going to compute using vectors. So a vector with its initial point at the origin is called a position vector. So we have a vector here in blue, and it's called a position vector because where we placed it. We placed it into our xy coordinate system, our xy plane, and its starting point or initial point is at the origin. So that's when we call it a position vector. When its end point is at some point a comma b, then we can write the vector, we can kind of rename it as a comma b in between two angled brackets. The angled brackets let you know that you're not just talking about this point, a comma b, you're actually talking about the vector that ends at that point. The number a is called the horizontal component, and the number b is called the vertical component of the vector. So a represents the horizontal or x component of your vector, and then b represents the vertical component of your, or y component of your vector. And then the positive angle between the x-axis and the position vector is called the direction angle, and that's represented in this picture by theta. So when you have a position vector, you have an angle formed with the positive x-axis, and so the angle theta is formed with the positive x-axis and wherever your vector is at. So the magnitude and direction angle of a vector, a comma b. So the magnitude or length, we talked about the magnitude and length in the last video, but now here's a formula for you to compute it. And so if you know the terminal point of your vector, you know your vector is a comma b in angled brackets, that means it ends at the point a comma b. Then this is how you find the length or the magnitude. You take your two components, horizontal and vertical, and you square them, you add them, and then you square root them. Essentially, it's just the Pythagorean theorem, if you want to think of it like that. It was your, if we formed a triangle with our vector, it was the one of the legs of the triangle squared plus the other leg of the triangle squared. And then you square root them, and that's going to give you the length or magnitude of the vector. And reminder from last time, when you see these two bars around your vector, that denotes the length or magnitude. Okay, so absolute value, think of them as absolute value bars, but when you're talking about vectors, you would read it as the magnitude. And then the direction angle, theta, is going to satisfy tangent theta is b over a, excuse me. So this is what we've already known from trig. If we formed a triangle with our vector, then this is the opposite side over the adjacent side, and that's going to give you tangent of your angle theta. So let's try out this example. Find the magnitude and direction angle for vector u equals 3, negative 2. So before we do any drawings, this is saying that I start my vector at the origin and then it ends at 3, negative 2. So here's what it looks like. My initial point is at the origin, my terminal point is at 3, negative 2, but then the angle theta, be careful about how you draw theta, because it's always going to be counterclockwise from the positive x-axis. So you start here at the positive x-axis and you go counterclockwise until you reach your vector. So that's theta. And so your magnitude, the formula we just wrote down, think about the forming a triangle here with your vector and the positive x-axis, and it's essentially the Pythagorean theorem. So our magnitude is the x or horizontal component squared, which is 3, plus the vertical component, negative 2 squared. So the magnitude or length of this vector is square root 13. So square root 13 is about 3.6. So the length of this vector is about 3.6 units. So our direction angle, remember we just talked about it in the last slide, it has to satisfy tangent theta is b over a. And so b is our vertical component or y component, A is the horizontal component or x component, so you just say tangent theta is -2/3, and then you just solve for theta. Okay, so if you use tangent inverse of -2/3, we're going to have to add 360 to it. So let me just remind you why. So tangent inverse is defined in quadrants 4 and 1, but it's defined as continuous angles from quadrant 4 to 1. So it actually uses your negative angle down here. Remember, tangent theta goes from -π/2 to +π/2. And so when you type this in the calculator, it's going to give you a negative angle because it's actually going to give you the angle going clockwise. So what you're going to do with that value is you're just going to add 360 to it, and that's going to give you your positive angle measure. So theta is 326.3 degrees. Now, another way to look at the horizontal and vertical components is to use this formula. So the horizontal component is equal to your magnitude of your vector times cosine theta. Your vertical component is equal to the magnitude of your vector times sine of theta. And this isn't a random formula. You can see why, and I'll show you. So if you look back at our position vector, just take a look at the horizontal component. So my claim is that it's the magnitude u times cosine theta. Well, think about what we know about our trig functions. Cosine of theta, if I wanted cosine of theta for this triangle in this picture, cosine of theta would be adjacent over hypotenuse. It would be cosine theta is a divided by u, or magnitude of u, okay, length of this vector. And so if I wanted to solve for a, I would just say, okay, cosine is equal to a over u, just times both sides by u, and that's how we come up with what a equals. Very same thing happens how you solve for b, the vertical component. And so now you can rewrite your vector involving the magnitude and the angles. There's a number of ways to write vectors, so I want to just make this clear right away. A lot of times you're just going to see this notation, the end point, the terminal point of your vector, and you're going to see your vector written with these angled brackets. But sometimes you want to write it in this form, where you use the magnitude or length of your vector and the angle, so cosine and sine of the angle that your vector forms with the positive x-axis. This is just two ways to write the same vector. One involves the terminal point, and the other one involves the length and the angle. Let's try this example. So vector W has magnitude 25, so 25 units, and then direction angle 41.7 degrees. Find the horizontal and vertical components. Now, before we even learned anything about vectors, you could solve this problem, but now we're just naming things in terms of vectors. So let me remind you, in the past, this example would have said something like, given this picture, find the adjacent side and the vertical opposite side of this triangle. So you already know how to do this, but it is just the formulas we talked about a moment ago. So our horizontal side, if you take cosine of this angle, 41.7, cosine is adjacent A over hypotenuse 25, and so if you just times by the hypotenuse, you get A. So you fill in your formula, you have 25 times cosine of your angle, which is about 18.7. So this horizontal component is 18.7. And then same thing with your vertical component, but this time using sine. So if you forget these formulas, just remember it comes straight from your trig identities, like what the trig functions mean. So you can say sine of my angle, 41.7, is equal to the opposite side over the hypotenuse, and then you can solve for the opposite side. So you just have 25 times sine 41.7. So the adjacent side is 16.6. And so you can rewrite your vector now in terms of those two components. And then that's the terminal point. So this vector ends at the point 18.7, 16.6. Let's do this example where we write each vector in the figure in the form a comma b. So we're trying to find, based on the directions here, the terminal point of the vectors. And there's 3 different vectors in this picture. So let's start with u. Notice what we have. The blue vector u, we know that it's length 5. It's magnitude 5. And if you kind of look closely here, it's the one that's at a 60-degree angle with the positive x-axis. So we know the angle that it forms with that positive x-axis, and we know its length, and that's enough to figure out how to write the vector. Okay, so magnitude times cosine of my angle is going to be the x or horizontal component. Magnitude times sine of my angle is the vertical component. And then we know these values. From our unit circle, we know cosine 60 is 1/2, and we know sine of 60 is square root 3 over 2. And then you just multiply both by 5, the magnitude, and so this is your vector. This is your vector in your angled bracket notation. So this point where it ends is 5/2, comma, 5 square root 3 over 2. Next, let's look at vector v. So notice where vector v is pointing, over here to the left. The angle is 180 degrees, formed with the positive x-axis, and its length 2, magnitude 2. So we fill in our format for our vector, the magnitude times cosine of the angle, comma, magnitude times sine of the angle. Before I keep going, you know these values, cosine of 180, sine of 180. Okay, hopefully you recognize what this was going to be. We end up getting negative 2, comma, 0 for this vector. And that one you can kind of tell just by looking. This vector is on the x-axis, it's pointing to the left, so it has to be a negative x value. Because it's length 2, it's got to end at negative 2 for the x, and because it's on the x-axis, it doesn't go up or down, so y has to be 0. Alright, our last vector here for figuring out the form of it is green, vector w. The magnitude is 6, and the angle here is 280 degrees. So same thing we've been doing, we're going to fill in our 2 components, vertical and horizontal. So our horizontal component is our magnitude 6 times cosine 280 degrees, vertical 6 times sine 280 degrees, and 280 degrees is not one of our familiar angles from our unit circle, so we're going to have just an estimate on this one. So if you use your calculator, you're going to get that this is about 1.0419, comma, negative 5.9088. Alright, so let's talk about some vector operations, things you can do with vectors. Just like you've learned operations with numbers, we're learning them with vectors. So this is just kind of my background sentence. I'm going to let all these letters A, B, C, D, and K represent real numbers. Alright, so when you add 2 vectors, so my first operation, if I have a vector and I want to add another vector, well, here's the result. In the last video, we did this geometrically. We drew how it looks to add 2 vectors. We had the parallelogram method, and we had the other method where we take the tail of one vector and put it on the head of the other vector. But this is algebraically how you find the sum. So you just take your horizontal component from your first vector and your horizontal component from your second vector, and you add them. And that forms the horizontal component of the new vector. And you do the same exact thing for the vertical components. If you have a number k, in this case a scalar, times your vector, well, it just multiplies both components. Whatever this number is that you're multiplying by, you multiply the horizontal component by it, and then also the vertical component. And we talked about this in the last video geometrically. This would change the length of your vector. It would either stretch it if k was bigger, or reduce it. It would like shrink it if k was smaller. And then if k was negative, it would change the direction by 180 degrees. If your vector is, with this notation, a sub 1 comma a sub 2, then negative u, so we just talked about this, is going to be negative a sub 1 comma negative a sub 2. So this is a combination of the rule we just talked about, and then what I was mentioning about changing direction. So this is just a scalar of negative 1. So you're just multiplying your components, your original components, by negative 1. But what that will look like if you were to draw it, your vector would change directions by 180 degrees. And then our last one here, if you want to subtract vectors, so one vector minus the other one, you actually can just think of it as addition of a negative, adding a negative. And so what you do is you take your horizontal component from your first vector, and then you say plus negative horizontal component on my second vector, and it basically just looks like regular subtraction. So my horizontal component from the first vector minus the horizontal component of the second vector. And you do that same thing for the vertical components. So let's try out these operations. So given my two vectors, u is -2, 1, and v is 4, 3, let's find the following a, b, c, and we'll draw them as well. So u plus v. Okay, and if you want to pause this and try these out on your own based on the operations we just discussed, go ahead and do that. Okay, so we're adding our two vectors, and remember what we discussed, you're just going to add individually the horizontal components and then separately the vertical components. So the horizontal components, -2 plus 4, and then the vertical was 1 plus 3. So our new vector, our resultant, is the vector 2, 4. So here's what that would look like along with the original two. So in the last video, we drew things like this, so hopefully this lines up with the image that you imagined. Your first vector was -2, 1, so it ends here, our terminal point is at -2, 1. V was 4, 3, and then here's the resultant. And so in the last video, we used the parallelogram method for one of our methods for drawing the sum. So if you can kind of picture, let's see if I can draw it actually, making a parallelogram here with your two vectors. The diagonal is going to be the resultant vector, or the sum. Okay, so let's try the next one. We're going to find part B, -2 times u. And so you just multiply both components of your vector u times -2. And then you end up with 4, -2. So before I show you what this looks like, think about how it's going to change. So we know what u looks like. It was this one down here. Timesing it by -2 is going to stretch its length by 2. It's going to double how long it looks, but then the negative sign is going to make it point in the opposite direction. So imagine what that's going to look like. Alright, so it's pointing exactly 180 degrees away from where u is pointing because of the negative, and it's twice as long as u was because it was being multiplied by 2. Alright, and let's try part C. So 3u minus 2v, so this is going to be timesing by scalars, 3 and -2, and then also performing this subtraction. Okay, so each vector gets multiplied by its scalar. In this case, 3 is going to think of it as just distributing into your vector. I'm going to keep the negative sign out and just distribute the 2 into the second vector. Okay, so we end up with -6, 3 minus 8, 6, and then we just subtract the components accordingly. So we have -6 minus 8, and then 3 minus 6. So the result here is -14, -3. Alright, so this image just has the steps for what we did, some of them. So we had our original 3 times u vector here, and then 2 times v. So notice if you look back at the other picture, the first picture, u was here, so 3 times u, it still points the same direction, but it's just longer, 3 times longer. V points in this direction. My picture's not quite to scale. If you notice, the tick marks are way closer together on my coordinate system here. So this is actually 2 times longer than this vector here. And so when we do the subtraction, even though we got this vector 8, 6, because we're subtracting it, think of it as like negative times this vector. We want to change the direction of it. So that's why we have -2v over here. And then you can think of them as adding the negative. So in the last slide, we talked about thinking of subtraction as adding a negative. And then here's your parallelogram rule again for adding. So if you add this negative vector, the diagonal is the result. Now let's discuss what are called unit vectors. So anytime you hear unit as a description, it means something with 1, the number 1. So like a unit fraction equals 1. Like 5/5 is really the number 1. It's a unit fraction. And so a unit vector has something to do with 1, and specifically its length or magnitude 1. So unit vectors, they always have length 1, magnitude 1. That's what it means. And there's two important unit vectors that we use, and they're called the I and j vectors. Okay, so the I vector, we use the letter I to denote the vector 1, 0. So it's the vector, the position vector starting at 0, 0, ending at 1, 0. And notice this is definitely length 1. We use j to denote the unit vector starting at 0, 0, and then we go up 1. So I and j are, by definition, these two vectors, 1, 0 for I and 0, 1 for j. Now why this matters is because this is now going to give you a new way to write your vectors. You can now write your vectors in terms of I and j. So any vector, a, b, can be expressed in this I, j form, or ai plus bj form, using the vectors that we just talked about. So if I have a vector that it has my terminal point at 3, 4, I could write it with my angled brackets 3, 4. Or now you have a new way to write vectors. And so what you can do is you can say, well, this means that this vector means I go 3 units horizontally, so 3 times I. Since I was only 1 unit, or length 1, if I times it by 3, I've gone 3 to the right, 3 horizontally. J is length 1, so if I times it by 4, I go up 4. And then if I connect these two, if I add these two, I get my vector u, because the sum of those two I and j vectors will give me this vector I'm talking about, this resultant. And so I just wanted to make it clear, this is now a new way to write your vectors. So sometimes, and it kind of depends on just like who you're talking to or what book you're looking at, you might see it written like this most of the time. Just know that it's the same thing as using your angled brackets. So you can say angled bracket 3, 4, or you can say 3i plus 4j. And so this is just what we were discussing. If v equals angled bracket a, b, then you can rewrite the same vector v using I and j. So it would be a times I plus b times j. Now the dot product is a new kind of product that you can compute with vectors. We haven't done it before. You've done products before, you've done multiplication. But dot product we haven't done unless you've learned vectors in the past. So the dot product of two vectors is denoted with this dot. And now be very careful. If you know you're talking about vectors and you just know it's a dot product, then you're going to compute it as the following. But if you're not sure, you might want to ask for clarity, because it does look like a multiply symbol. It usually is drawn a little bigger, like maybe the dot is just like really large so that you know it's a dot product, but just be aware it's not a multiplication sign. It looks like it, but it's usually written a little bit bigger, or someone will just tell you that it's a dot product. So when I read this, I don't say u times v, because that would be regular multiplication. I read it as u dot v. Okay, so if I know it's a dot product, I read it as u dot v. And here's how you compute it. U dot v is the horizontal component from the first vector times the horizontal component of the second vector. So you multiply the two horizontal components. Then you add the product of the two vertical components. So you times the vertical component b times the vertical component d, and you add those two. And whenever you compute the dot product, and this is kind of a way to double check yourself, the answer is a number. Because there's things we do with vectors where we do operations and compute and we get vectors as answers. But anytime you compute a dot product, your answer needs to be just a regular number. It's a scalar. It's not a vector. The answer here is a number. So here's how we're going to test this out. So let's see what we can come up with. So find each dot product. If this didn't say the word dot product, and you were just it said find, and then you had parts A and B, You can kind of assume it's the dot product because you're dealing with vectors. But if you're ever not sure, you can ask for clarity. So 2, 3 dot 4, negative 1. So how this works is I take my 2 horizontal components and I multiply them, and then I add my 2 vertical components and I add that. So 2 times 4 plus 3 times negative 1. So multiply the horizontal components, multiply the vertical components, and add. And then notice we are going to just get a number. So the dot product is 5. So if you want to, pause this and see if you can compute part B before I do. So we're going to multiply the horizontal components together and the vertical components and add them. So this one we get 0 as our dot product. So properties of the dot product. So our vectors are denoted with bold print, U, V, and W, and then K is just a real number. Okay? And so these are properties that are true for dot products. You can switch the order. Dot product is commutative. So U dot V will give you the same answer as V dot U. The dot product you can distribute. So notice what this kind of looks like. It looks like distributing into the parentheses. So U dot V plus W. You can take this U and you can dot it with V, dot it with W, and then add them. So the best way to think about this is just think of it like distributing the dot product. Same thing from behind. So U dot plus V, and then you dot W in the back. Think of distributing from the back. So you can bring this dot W into U and also to V. So U dot W plus V dot W. Now if you multiply a vector times a number K, so it's times a scalar, and then you dot it, you can switch the order quite a bit. So the scalar times your vector, you can take the scalar out and do the dot product first. So you can dot your 2 vectors, U and V first, and then times it by K. Or you can take this number K and put it on your second vector. And so you can times it by V and then find the dot product. Any of these 3 will give you the same answer. 0 dotted with U is 0. Now I want you to just be aware here. This is the 0, this is number 0. This is just the number 0 dotted with our vector U. The answer is the number 0. If you were doing something with the 0 vector, not dot product, because I talked about the dot product will give you a number answer, but just be aware that this is not the 0 vector, because one way to know is that this is not bold print. Vectors we use bold print or the vector arrow on top. We can use like this little arrow if it's going to be a vector, but it's not. This is just a number. The other way to know is that the dot product is just always going to give you a number. And then if you have 2 of the same vector, so if you have your vector and you dot it with itself, it's actually the same value as if you find the magnitude and you square it. So let's say you wanted the dot product of a vector in itself, but you already knew the magnitude, then you could just take your magnitude, square it, and that's your answer. Now the geometric interpretation of the dot product. So we just talked about the dot product, how you compute it, but here's part of how to represent what it is. So if theta is the angle between the 2 non-zero vectors U and V, so you have 2 vectors, they have a common point, a common initial point, and then there's an angle between them. That angle is theta. So it has to be between 0 and 180. Then the following is true. So this is where the dot product is used. So we know how to compute it now, but it has to do with the angle between the vectors. So cosine of the angle between the 2 vectors is equal to the dot product of the vectors divided by their magnitudes being multiplied. So essentially what you can do here is you can rearrange this. If you just want to solve for the dot product represents, so U dot V is equal to the 2 magnitudes being multiplied. You can times by them here, times cosine theta. So let's try this out. Find the angle theta between 2 vectors. U is 3, 4, and V is 2, 1. Now I can draw this and try to come up with the angle between them just by my drawing, but we have a formula we just discussed, so we're going to use that. So I know that cosine of my angle theta between two vectors is equal to this quantity. And so I can compute everything in this quantity. So the numerator is my two vectors getting dotted, their dot product. And then the bottom of the denominator here is the individual magnitudes. So I need to compute the magnitude of this vector times it by the magnitude of this vector. So go ahead and pause this and try to compute it before I show you. Alright, so our dot product on top was 3 times 2 plus 4 times 1. And then on bottom, remember how to find the magnitudes. You take the components, you square them, so 3 squared, and then you add plus 4 squared for the first one. The second one was 2 squared plus 1 squared, and you add, and then you take those square roots. And so if we simplify, we get 10 on top, and then 5 square root 5 on bottom after simplifying a little bit. And technically I could say that this is 2 over square root 5, just to simplify a little more. And then if you take cosine inverse, because remember what this was giving you. This was giving you cosine of your angle. But the question was, what is the angle? So this is not the answer until you take cosine inverse. So cosine inverse of this value, your angle between your two vectors is about 26.57 degrees. Let's do this again with two new vectors. So find the angle between the two vectors, 2, -6 and 6, 2. So if you want to, pause this and try to work this out before I show you any of the steps. Okay, so here's our formula, filling in our vectors. So dot product between the vectors on top, magnitudes individually of the two vectors on bottom, and you multiply those magnitudes. And so on top, 2 times 6 plus -6 times 2. On bottom, this was 2 squared plus -6 squared. And then this was 6 squared plus 2 squared. And this is a little misleading, this dot product symbol. Let's see if I can, it's not a dot product. At this moment it's a times sign, but it's not, it's too big. It's a little misleading. So this is just times. So I'll just get rid of that. Okay. And then we get 0. So the numerator is 0, the bottom's a different number. So this 0 out of 40 is just 0. And so still you need to do cosine inverse. So cosine inverse gives you theta. So cosine inverse of 0 is 90 degrees. So the angle between these two vectors is 90 degrees. And what's interesting is when the angle is 90 degrees between the vectors, the dot product is 0. So let's sum up the information about the dot product. So for angles theta between 0 and 180, we have some different things that will happen. Cosine theta is positive if your angle is less than 90. So if the angle is acute, cosine theta is positive, and therefore your dot product is positive. Or you can say because the dot product is positive, cosine theta is positive. Cosine theta is 0 when theta is 90. So if you have a right angle, if you have exactly 90 degrees between your vectors, your cosine theta is 0 and your dot product is 0. And then anytime cosine theta is negative, it's because your angle is greater than 90, or you have an obtuse angle between your vectors. And so the cosine is negative and the dot product is negative. And so the middle case here, when we get 0, is a little bit interesting. So if u dot v is 0, it's for two vectors, non-zero vectors, and that's because cosine theta is 0, meaning that theta is 90. And so what this represents is your two vectors are actually perpendicular or orthogonal. So you can tell without actually drawing, if you compute the dot product between two vectors and you get 0, you can tell that the two vectors that you have, they're orthogonal or perpendicular to each other. And that's it.